We are now going to return to our article about spacetime algebra after a divergence into 3D geometric algebra and also an examination of rotors. And that's just a very important first step when it comes to rotors. But we're now going to start this section 3.6, which is very, very important. And then rotors will become important again when we hit section 3.7. Just as a bit of foreshadowing, our rotors all dealt with a pseudoscalar that's squared to -1. And there's an important reason for this, right? That allowed us to write things in terms of e to the I, and then we chose an angle of rotation over 2. That was our sort of rotor, right? That was our definition of a rotor. But strangely enough, there are bivectors in the spacetime algebra that square to +1, and that will make things extremely different. You can still write it in exactly this form, but the breakdown is hyperbolic cosine pi over 2 plus a hyperbolic sine of phi over 2 times I, where I squared equals +1. And this will correspond ultimately to Lorentz transformations in well, they correspond to the Lorentz transformations that we call boosts, right? So we have yet to do a whole other layer, but all of the machinery was laid in our last lesson because the math is the same, it's just the Euler form is different, and special relativity all lies in that. This one little thing, this I squared equals +1, that means this bivector that defines the plane of rotation has to have a +1 signature, not a -1 signature. And the reason that's important, we're going to start seeing today as we talk about relative frames and paravectors. So it's just a bit of foreshadowing. So with all that in mind, let's begin. And we will read from section 3.6, relative frames and paravectors. So just when we look at this, we better understand two concepts here, relative frames and paravectors. Those are obviously two different things. We're expecting paravectors to be elements of the algebra C13. We're expecting that. Relative frames, however, is something that we're thinking of, oh, gee, that sounds like special relativity. That actually sounds like physics. So optimistically, when we read this, we're thinking, okay, we're going to get some physics, right? This will be the physics, and this will be the mathematics. And apparently, we know about regular vectors, right? We know about multivectors. So there's going to be something out there called paravectors, right? And well, we know that everything in the algebra is a multivector. So some of these multivectors we're going to call paravectors. And we know about dual vectors, right? We have a vector and we take its dual, but we know that those are really trivectors. So it's kind of hard to imagine, how are we going to find a new type of vector in this mix, right? And is it going to be something relevant, or is it just going to be something semantic? So it's kind of exciting. When I see something like this, I get like, oh, wow, I just sitting here by myself, I can't imagine what it would be. So it motivates me to read it. So to begin, to connect the spacetime algebra, C13, right? So this is the symbol for the spacetime algebra. Remember, it's been a while since we've done this, but C means Clifford algebra. 1 is the number of basis vectors whose square is +1, and 3 is the number of basis vectors whose square is -1. Sometimes, by the way, you'll see a 0 here because there's also the possibility of basis vectors squaring to 0. And in our algebra, there's none of those. But you could imagine in principle that there would be a 1 there, in which case you would have an E4 squared equals 0, which is really interesting. It's kind of hard to imagine what good that would be, but it is actually very good, right? We discussed very briefly that the spacetime algebra, we also have these, what do we call them, projective geometric algebras, right? Those have things that square to 0. Anyway, so this is a reminder of what this symbol means. So to connect the spacetime algebra with standard 3D vector analysis, we express the duality of the spacetime algebra in another way that selects a particular inertial frame. All right, so let's dig through this statement. First of all, spacetime algebra is four-dimensional. Standard 3D vector analysis, well, that's what we've kind of been talking about for the rest of the for the previous couple lessons, right? This is where we have cross products, where we have dot products. This is where we have projection and rejection. And we've taken that and we've cast it into a 3D geometric analysis, right? 3D geometric algebra. So there's two ways that this sentence can lead us on, right? We're thinking, okay, we've got our space-time algebra, which is 4D. Well, I can connect it to the familiar world of cross products, dot products, and regular standard vectors that live in a three-dimensional space. And this is all your basic physics, basic engineering, physics. Well, I guess the way to think of it is not basic engineering physics, right? It's how do I say it without insulting engineers? Basic. Let's say basic. I don't even want to say basic physics. How about elementary physics? Elementary physics, right? This is your first year physics and stuff like that, and all of engineering, right? Because all of engineering is done in the same world as elementary physics. But that's not what this chart was supposed to be, right? So this chart is we're trying to make, if you take this literally, right, we're trying to make the connection between space-time algebra and standard 3 vector analysis. Well, this is standard 3 vector analysis. But you could also think of this as, well, wait a minute, standard 3 vector analysis is 3D geometric algebra, right? There's a connection between these two, which we studied a little bit in the last couple lectures. And we didn't go very far into it. Like, we didn't do any examples of real physical problems solved using 3D geometric analysis, things that you would know that would be trivial based on our experience with this. We never did any demonstrations of those trivial things down here. That's just not the point of our work. We're just trying to discover the mathematics behind it. So the question is this paper going to connect space-time algebra to this stuff, literally, or to this stuff? And in some sense, it doesn't really matter because this connection exists. However, as a little bit of foreshadowing, we really want to do it this way, right? We want to show how the 3D geometric algebra exists inside the 4D space-time algebra. And then, if you're really interested, you make this connection yourself. All right, so the way they state it here is they talk about the standard 3 vector analysis. But I think what we're really going to see is actually that they're really connecting the 4D space-time algebra to the 3D geometric algebra that has a Euclidean metric, right? The Euclidean metric, which is essentially the geometric algebra of elementary physics. Okay, phew. So then it talks about we're going to select a particular inertial frame. Okay, so this is really important, right? Because selecting a particular inertial frame, that's very special relativity language. So let's discuss that. So if this whiteboard is my space-time, and it has some three-dimensional layout, we'll give it a three-dimensional coordinate system. So this is X, Y, and Z, right? So this is our regular three-dimensional space. How we studied, this is the way we studied special relativity. Well, this is one way to study special relativity. The other way to study special relativity is to include a time axis, and you're dealing with essentially four-dimensional Minkowski space. So let's do it that way, four-dimensional Minkowski space. And this is our spatial direction. We'll call it X. And this is our time direction. We'll call T. Now notice, just by drawing this X and this T, I have established an inertial frame in the context of special relativity. And the reason is because if I am motionless in this, with respect to this inertial frame, that is, if I, say, lived right here in space, but I had no motion relative to this coordinate system, then, well, I'm really not motionless, right? Because I'm moving in time in this upward direction. In fact, I'm moving in time with a 4 velocity v, and in a system where the speed of light is normalized to the unitless number 1, that magnitude of that velocity v is always going to be c. All 4 velocities have a magnitude of c. So that's the one point we need to remember, is no matter what you are, no matter where you are, no matter what your state of motion is, right? As long as you have some 4 velocity, you will always have a 4 velocity. Any particle with any path through this inertial frame will always have a 4 velocity v, and I can't put a little vector symbol on it anymore, right? It is a 4 vector, though, which means it is expressible, totally expressible in our system as, v1 gamma 1 plus v2 gamma 2 plus v3 gamma 3 plus v0 gamma 0, right? That is the 4 velocity. And if you take the magnitude of this 4 velocity, you should always get 1, which is the speed of light, right? That's just a basic physics principle that's really important to come here already understanding. If you don't understand that the 4 velocity of all objects in all states of motion, the magnitude of that 4 velocity is 1, then you're a little bit behind, and the study of the spacetime algebra is probably a little outside of your preparatory zone. So make sure you're comfortable with this particular point. It's very important. And also, keeping this in the forefront of your mind is also important, because even if you do understand special relativity and you kind of remember this, it never was super duper important, but understanding that the magnitude of your 4 velocity is also always 1 really kind of makes time dilation and space contraction sort of sensible, because you can understand that no matter where you are, if your 4 velocity is 1, although I got to admit there's some places here where your 4 velocity is bigger than 1. I have a feeling, maybe not. Right, any place where this line would go over 45 degrees, right, your magnitude, your 4 velocity would be, well, you'd be traveling faster than the speed of light, right? So, but it shows you how your 4 velocity is distributed between velocity in time and velocity in space. So if this 4 velocity is always the same, your velocity through time is different than your velocity through space, and this is where time dilation can come from. And so we have things like the rate of change of the time coordinate with your proper time, right, which is an important ratio, right, an important ratio in special relativity. All this should be familiar. But the point is when we've picked an inertial frame, we've actually basically laid down these coordinates. And we can pick another inertial frame, right? We could pick a totally different inertial frame. We could go, there's an object that might be moving at uniform velocity in the green inertial frame, and you have this blue object. Well, we can transfer to that blue inertial frame and find a new frame where we're motionless with respect to this moving object, right? Where the object's obviously moving in the green inertial frame, but now we're motionless with respect to that object, and the green inertial frame suddenly is moving, the other way, and it becomes essentially this is a Lorentz boost transformation. So this is sort of a recap of the things that we're going to be talking about, right? We can boost from the green frame, right, to the blue frame, and these are inertial frames because their motion is uniform. Now, we're not talking about gravity, so if we included general relativity, the notion of an inertial frame gets expanded to anything that's in free fall. And of course, everything becomes a lot more intricate and a lot more interesting. But in special relativity, which is what we're dealing with in our space-time algebra, there's no gravitational forces. Well, there's no gravitational curvature to the space-time. There's no curvature at all to the space-time, gravitational or otherwise. It is a flat space-time, Minkowski metric everywhere. And choosing an inertial frame is essentially choosing this time direction, right? Because if we choose this time direction, we're saying that anything that's stationary in this inertial frame, its forward velocity is entirely in that time direction only. It's not moving in the space direction. So that other things could be moving, right, relative to it, but by choosing an inertial frame, we are essentially choosing this vector, right, this time vector, how it's pointing. So when we go to this, it's saying we express the duality of the space-time algebra in another way that selects a particular inertial frame. So this word duality is now on the table. And we've already learned about a form of duality, right? Right multiplication by, take any multivector, right multiplication by I creates its dual, right? Creates the dual of M. And we use this to great effect, right? We created the notion of a complex scalar, which was alpha plus the dual of a real number, right? So it's a 0 blade plus a 4 blade. And we created the dual of a vector. Right? We took I think, what did we say? We said Z was a complex vector, which was a vector V plus a vector, the dual of a vector W. And we know that this is a trivector. And we wrote all of our multivectors in the form of, or we learned that we could write all of our multivectors in the form of zeta plus Z, right, plus a bivector, right? And to be clear, the bivectors also could be written in complex form, right? Because we could say the complex form of a bivector, we write as C, it's a regular bivector plus the dual of a different set of regular bivectors, where all of these bivectors are created out of three basis bivectors. Say, we choose three of the basis bivectors, B1, B2, and B3. And these guys are made out of just the duals, B1 dual, B2 dual, B3 dual, right? That's how we make these guys. And we end up with all of the six basis bivectors, but we've kind of broken it up into a vector and a bivector and a complex bivector, utilizing the fact that if C is some sort of grade 2 object, it's going to be the sum of bivectors, and bivectors are dual to themselves. So we didn't actually do that. We only talked really about these as far as being, we only talked about complex vectors and complex scalars. We didn't really talk about complex bivectors. But the point is that was the type of duality we've already learned about. And this duality was just a bunch of maps from C13 into itself, right? It was just maps of C13 back into C13 that kind of split C13 into these two halves, right? We saw a few charts of that before. Right, here was the chart we saw. This duality took our entire space-time algebra, well, at least the basis of the entire space-time algebra. If you imagine this is the basis, these particular bivectors and these particular vectors and the unit scalar. If you imagine the whole part of the multivector space spanned by these objects as being on the left side and the whole space spanned by these objects on the right, you can see that this duality, this right multiplication by I, splits the space into two. And that's an important duality that we now use. Here, by the way, is the notion of the bivectors and their duals, and these span all possible bivectors in the all of the multivectors all of the grade 2 multivectors are spanned by these objects. and we're using this duality. So now we're going to learn about another duality, another type of way of dividing the space into two parts. That's the promise. And that promise is this new duality is going to select a particular inertial reference frame. A particular inertial reference frame. So this duality is not just splitting it's not coming totally for free. The one we've studied is just literally a way of, well, we're just going to make full use of this notion of I as gamma 0, 1, 2, 3, and we're going to use this sort of bookkeeping technique to split the space. But now we're doing more than that. We're not just doing a bookkeeping. We're going to split the space, so it's always going to be bookkeeping in that sense, but it's also going to cast a little bit of physics in there. So that's what we're expecting, right? So let's move on. Okay, so to continue. To do this, we decompose the bivector basis into the three elements that involve a specific timelike vector gamma 0. So here's what they want to do. They want to say, okay, we know our bivector basis looks like this. That is, we know that these are the 6 bivector basis vectors, but we're just going to take the ones that have the space-like part second, right? So this is gamma 1, gamma 0, for example. We put the space-like one second. And those are going to be our first 3, right? We're going to break those out. And these are the second 3. Now notice, I've been saying a few times in the past, I wonder why they didn't use 2, 3, and 1, 3, and 1, 2. And why isn't it 0, 1, 0, 2, 0, 3? That's so standard in the business of tensor analysis and the study of forms. They always have these increasing indices, but not in space-time algebra. They don't. Well, now I think we're slowly becoming aware of why not. First of all, they value this. They value this for some reason that we're going to learn. And they value it so much that they're going to take these guys right here, which are those guys, which are these 3 vectors here indicated underline, and they're going to actually give them special names. They're going to call them sigma 1 with a vector arrow, sigma 2 with a vector arrow, and sigma 3 with a vector arrow. So they've taken these 3 and singled them out as being important. And once they've done that, well, then we use the other duality, right? We use the other duality, I'll say it in red, right? We do the other duality and we form sigma 1, 0, I, right? And that gives us sigma 3, 2. And then this other duality, sigma 2, 0, I, gives us sigma 3, 1. And then the duality we've already learned, sigma 3, 0, I, gives us sigma 2, 1. And that is why they chose this particular basis in this paper. It's a bit of an anticipation, right? They're anticipating the significance of this particular set of 3 bivectors, a significance we haven't learned about yet. But in anticipation of that, this is why they've chosen these guys as being part of the basis. And then the duality, the right duality of multiplying by I, well, that's going to automatically give us these 3 guys. And it spares us some negative signs. So if I could have written this as minus gamma 2, 3 and called that the basis vector, but then I got to carry around that minus sign. And who wants to do that, right? So this is the answer to the question of why they chose this particular index prescription. It has to do with this notion of relative frames and paravectors that they're introducing now. So to do this, we decompose the bivector basis into the 3 elements that involve the specific timelike vector gamma 0, which are these 3, and then the next part of the paragraph, which is on the next page, and their duals, which are these 3. So now they've broken down the basis into 2 halves. And by the way, they already did this. Right back up here, when they split the space up to demonstrate the dual, they had already laid the foundation for this, right? Because they already said, well, we're going to choose these 3 basis vectors and their duals, right? So they've actually kind of already set this up. Here they didn't tell you that there was anything physically significant about these, and in fact isn't anything physically significant about these in this particular presentation, because it isn't until you realize that these vectors, you really have to select gamma 0 as some special vector, and everything we'll see in this form of duality depends on gamma 0 being of unique significance. And that unique significance is essentially, it is the velocity, the fore velocity of the inertial frame that you're sitting in, right? If gamma 0 is equal to your fore velocity, you've gone into the inertial frame of a particular inertial frame. You've chosen a particular inertial frame, and that frame is motionless in itself, right? It is motionless with respect to its own spatial positionings, and it's not motionless with respect to its time vector, though. So that's sort of the point here. Okay, so so the first thing is to split the basis vector like this, right? Now we're going to try to understand the significance of that split. Okay, moving on to the next sentence with I equals 1, 2, 3 and their duals. So we've already discussed this, right? So we've split up the entire space-time algebra into sigma I and their duals, sigma I, capital I. So, and these are all bivectors, right? These are all bivectors. Now they use this Levi-Civita form to sort of flush out what this dual is. That's not very enlightening. You know, I'm very nitpicky about some things about the way things are written. This does not actually illuminate anything. If you've gotten to this part of the paper, you need to know that if you write multiply by I, you're dealing with the dual. This doesn't help really remind you how to calculate the dual anyway, because most people, when they calculate the dual, they're just going to say, okay, well, then let me see. I is gamma 0, 1, 2, 3. Sigma I is gamma I, gamma 0, and this dual is going to be, and then you kind of run it in your head, right? And so, you know, throwing this in there doesn't really remind you of anything particularly useful. So I would put that in there. But the point is that we've broken the space-time algebra into these two pieces, right? These guys here and these guys there. And then the paper says we're going to give that a name. We're going to call that division, this division into two parts of the bivector basis. Remember, this is just the bivector basis. This guy here is a bivector, right? We're going to call it the space-time split of the bivector basis. Thank you for mentioning that, the bivector basis, into an inertial frame, and it's illustrated in figure 6a. We'll get to figure 6a in a moment. It's a good figure. All the figures on this chart are really good. Save that problem with the minus sign on that one chart that talks about the Hodge dual and Hodge duality. I'm going to have to go back to that and kind of figure out what that's all about. I'm sure it's buried in the definition of a Hodge dual that I'm missing something. But it's not that important. Because for us, the duality, the elementary duality, which we'll call Hodge duality, is right multiplication by I. Now we're creating a new form of duality. We have yet to fully manifest it, but it starts by understanding that there's this split in the bivector basis. So the elements of sigma I, directly correspond to the three spatial directions gamma I orthogonal to gamma 0. Okay, so this is kind of an interesting sentence, right? The elements of sigma I directly correspond to the three spatial directions gamma I. Okay, there's only three spatial directions. There's gamma 1, gamma 2, gamma 3. And these are now bases for the grade 1 part of the algebra. This is basis for the grade 2 part. This is basis for the grade 1 part, missing gamma 0. But the three spatial ones, right? The three spatial ones directly correspond to these guys right here. So this is kind of strange. What could they possibly mean? Well, it's kind of obvious what they mean, right? You know, sigma I is clearly, let me erase some stuff here. We know that sigma I equals gamma I, gamma 0. right? So sure, every gamma I on the right corresponds to exactly one sigma on the left. So that's the direct correspondence. They want you to think of this direct correspondence. Well, this is the definition, right? So, but what the correspondence is, well, this corresponds, we're just going to say it somehow corresponds directly to gamma I. Well, what is the correspondence? Well, as you're going to see, the obvious correspondence is right multiplication of gamma I by sigma 0 actually equals sigma I, right? So the correspondence is through this multiplication by this special vector gamma I. That's what makes the connection between sigma I and or gamma I and sigma I. It's multiplication by gamma 0. So gamma 0 is specially picked out here to establish this correspondence, right? And now the sentence isn't that great, right? So here's the sentence. It's not that good because if you grammatically parse this sentence, you're writing the elements of sigma I directly correspond to the three spatial directions gamma 0. I'd put a period right there. Orthogonal to gamma 0 is, well, it's not very meaningful, right? Because every sigma I is orthogonal to gamma 0. It's not like there's 5 different sigma I's, right? And only 3 of them are orthogonal to gamma 0. And therefore, we've got to find the particular gamma I's orthogonal to gamma 0 to establish this correspondence. So we're not hunting and pecking for spatial directions that are orthogonal to gamma 0, right? They're all orthogonal to gamma 0, right? So this part of the sentence not only does it not add anything, it actually confuses things because you might think for a second, wait a minute, did I miss something? Are there gamma I's that are not orthogonal to gamma 0? And there are none, right? Those don't exist. So that's got to go away. All right, so let's read the next sentence. The next sentence begins with the word importantly. And when you see that word importantly, big trigger, okay? Importantly, they will act as a basis for the 3 vector quantities that are used in standard vector analysis treatments of electromagnetism, period. Okay, so before we dive into the sentence, what the heck is they, right? They, of course, is sigma I, right? And here's a big tip. Don't use pronouns, right? Don't use pronouns. I'm not going to say anything else about that. I've kind of reached a point where, if I have a pronoun in my writing, I just get rid of it. I just find a way to not use pronouns. And the easiest way not to use a pronoun is to just put what it is in there. Would it really does that pronoun save you anything from writing sigma I there? And what the heck is they, right? I mean, it could be referring to the spatial directions gamma I, right? But no, they're referring to this. So there's a real thing in the text closer to the pronoun than what the pronoun actually refers to, right? So that's bad. So just don't use pronouns ever. Never use pronouns. Okay, never mind. So let's move on about that. Sorry. So importantly, they will act as a basis. Sigma I will act as a basis for the 3 vector quantities that are used in standard vector analysis treatment of electromagnetism. Okay, so if I just took that sentence in isolation, I'm thinking, wow, okay. Basis for the 3, what's a 3 vector quantity used in standard vector analysis treatment of electromagnetism? Can I think of one? Well, sure, I can think of the electric field, right? So the electric field is a vector quantity. I'll put a little vector on it. And in my standard treatment, I think of it as EX I hat. I'll do a little nod to engineers, right? And use their notation, EY J hat plus EZ what's it, K hat? Do they use K, right? And say, well, I've used that in my elementary introduction to electromagnetism, right? Even later undergraduate physics courses are using this kind of vector expression for the electromagnetic field. But what it says now is they will act as a basis for the 3 vector quantities used in standard vector analysis. Well, here's the basis, IJK. Are they really saying that I can write this as EX sigma 1 plus EY sigma 2 plus E Z sigma 3. Is that what they're saying? And yeah, that is exactly what they're saying. And then the obvious point is, but wait a minute, sigma are bivectors. They're not vectors. They're bivectors. So how can this be a basis for a 3-vector quantity? First of all, there's 6 of these things, aren't there? They say, no, there's only 3. Sigma I, there's only 3 of them because we've split our basis. Our basis has been split into sigma I and sigma I dual. Right? So we've split our basis. So we only have 3 basis vectors. So the dimensionality is right. And we even put these little vector symbols on them. So that's something that goes back to elementary vector days. So that's the claim that they're making. So we'll see how that flushes out as we move through the material. As such, we notate these basis elements. Okay, again, problem with the pronoun. We notate these basis elements. We notate sigma I. That's all you got to say. I just saved 3 words right there. By my basic rule, don't use pronouns. I saved clarity and words. As such, we notate sigma I using standard vector arrows and refer to them as relative 3 vectors. So we're going to refer to these now as relative 3, I guess, basis vectors. And what they're really saying is that E that I wrote down, right? That E that I wrote down, which was, I guess I could write it as EI sigma I, like that, if I used Einstein's summation notation, which I'm allowed to do. I'm allowed to do that. E is a relative 3 vector. This is a relative 3 vector because it is built out of these new basis elements, this split in the bivector basis. So we're going to just call this guy a relative 3 vector, right? As opposed to a 4 vector, right? See, and we have that problem with 4 vectors, right? Because a 4 vector, in terms of the multivector, in terms of being a multivector, is actually a grade 4 object. But a 4 vector, in the terms of special relativity, is just something that's written as VI gamma. Well, I guess V mu gamma mu, where mu goes to 0, 1, 2, and 3, right? So that's a special relativity 4 vector, right? So we don't, the name they're going to give to that, I believe, is a proper vector, right? A proper vector is going to be a grade 1 object in the space-time algebra, right? Where a relative 3 vector is actually a bivector in the space-time algebra because the sigmas are, in fact, bivectors. But we're going to call them relative 3 vectors because, first of all, due to the split, these guys are coming out of a subspace of dimensionality 3. So that's where this number 3 comes from. And they're vectors in the sense that they connect to regular vectors of the standard treatment of standard electromagnetism. The regular vanilla 3-dimensional Gibbs Heaviside vector analysis. Okay, so reading on. Geometrically, one can conceptualize the relative 3 vectors that are experienced by an inertial observer as plane segments in spacetime that are attained by dragging the spatial frame gamma I along the timelike direction gamma 0 of the observer's world line. As we will make clear in section 3.8, the 3 vectors sigma I also have a deep connection to the standard Pauli spin matrices, which motivates our choice of notation. All right, so now they're trying to give us a slight interpretation here, which they probably don't spend enough time on, right? Enough time on, because this notion of dragging a spatial frame gamma I in the timelike direction gamma 0 of the observer's world line. Well, that's what a bivector is, right? You know, we already kind of know that if we have a say, gamma I is just this basic bivector. And we know that if we sweep it in the direction of gamma 0, right, we end up with this bivector, gamma 0, or gamma I0. The way I've written the handedness, right, with this circulation was I0. So we know that that's what this bivector literally is, right? So we know that sigma I is literally this bivector, and that literally can be interpreted as the bivector where you take gamma I and sweep through gamma 0. Now what the space-time interpretation is, okay, now we're calling this the time axis, right? We're calling that the unit vector along the time axis in Minkowski spacetime, right? Four-dimensional Minkowski spacetime, right? Which has these vectors. Well, you know, if I'm an object that lives at one unit along the I-axis, right? And I don't move. I never change my physical position. Well, I do move, right? I do move through time, right? So the vector that locates my position in space-time is constantly sweeping along in time, right? And so these bivectors, to call my position in space, right, a bivector, actually kind of absorbs the fact that I'm moving in time by physics, right? By the premise of space-time physics, the premise of special relativity is that we're always moving in time. It's not a literally stated premise in the sort of axiomatic development of the theory, but it's something that we discover based on the idea that C equals 1 in all reference frames, and that there's no special coordinate system. You learn, well, that implies that we all have movement in a four-dimensional Minkowski spacetime, and we're all moving through time. And we all know that our four velocities are always equal to c. Those things are all sort of derived thoughts. And I'm sure you could go either way. You could use those as axioms and create the rest of special relativity. It's not typically done that way. But what suddenly we realize is that if I position something in space using these guys, right, instead of these guys, right? So say I say the position of my object is x1 gamma 1 plus x2 gamma 2 plus x3 gamma 3. That definitely puts it in a certain place in space, but space-time is four-dimensional, so to really catch it, I've got to add this x0 gamma 0, and that creates something that exists for one instant in time, just a flash, just a moment, right? And after this, so this is what we typically call an event in space-time. But real physics doesn't, real physics, this is the real physics, by the way, but elementary physics doesn't make this notion of having time as a coordinate. In standard physics, this is all gone. This piece is gone, and we just talk about something that's located at a spot in space. Well, in space-time algebra, you can kind of do that if you absorb this motion of time into the very definition of the basis vectors, and that is what we're doing here. It's actually very profound and very interesting, right? Because these bivectors actually include this sweeping motion through time, and it does allow you to say that, hey, my position in space, r, is ri sigma I. And I'm sitting still there, right? I'm sitting still there, and somehow the movement through time is captured through sigma. And that's, I think, what they're trying to get at here. Geometrically, one can conceptualize the relative three vectors that are experienced by an inertial observer as plane segments in space-time that are obtained by dragging the spatial frame gamma I along the timelike direction gamma 0 of the observer's world line, right? And so we're thinking, okay, we've established a frame, we've established gamma 0, that's my world line. My world line, I'm the observer, I'm in an inertial frame, my world line goes straight up because it's my inertial frame. So I'm motionless in my own inertial frame. So I don't have any movement in the gamma I direction. And so if I see something out there in gamma I away from me, well, that thing's moving with me because it's also motionless and it's sweeping out this plane. And it makes a lot more sense for me to locate it if all I'm doing is thinking in three-dimensional space terms. If I locate it with sigma I, that bivector catches the fact that it and I are both moving through time at exactly the same rate because we're motionless together. I mean, we have relatively no motion. And then they do this tease here. They say, we'll make it clear later, section 3.8, that these three vectors are deconnections to the Pauli spin matrices, which motivates our choice of notation, right? So the sigma, sigma I is the typical notation for the various Pauli spin matrices. And so that's why they've done this, which also, and remember, they've already made this maneuver with gamma mu, right? Those are similar to the Dirac matrices, which are four-dimensional matrices. These are 2 by 2. These are 4 by 4. So they're setting up the notation to be useful later on and to be familiar later on. Okay. All right, before we close for this lesson, let's have a quick look at the figure 6 that they are interested in us seeing. So what they've done here is, okay, they're talking about the space-time split. So they're showing us in this figure half of the algebra, right? The three bivectors are now renamed. These three timelike bivectors are now renamed. Sigma 1, sigma 2, sigma 3. And why are they timelike, by the way? Recall that if I took gamma 1 as gamma 1, 0, and I square it, once I square it, I got to flip the gamma zeros once, the gamma 1, 0 once to line up these two gamma zeros. Those square to positive 1. Then the 1s square to negative 1, which cancels the negative sign I got from the swap. So the answer is plus 1, which means the magnitude of sigma 1 is actually plus 1. And therefore, it's being greater than 0. It's timelike in this system. But the point is the space-time split takes those timelike bivectors, all of the grade 1 basis vectors, and the scalar basis vector, and it puts that into half of the space-time. So everything that is a subset of this stuff, or the spanning of all of this, is in this split. And you could ask, well, is this exactly half the algebra? Well, I can take the duals of these guys, right? I can take the duals of these guys and get the other half, and that's three basis vectors for the other half of the bivector basis. I can take the duals of these guys and I get all the trivectors, and I take the dual of this and I get the quad vector. So yeah, this is exactly half of the space-time algebra is before us there. So then what we haven't studied yet is the relative frame duality, but so now it's inside the space-time split. If we just study this, well, what do we see? Well, if I multiply any member of the bivector basis of the space-time split and the scalar part, if I multiply by gamma 0, I get the gamma 0 part of the space-time split. And when you multiply these guys by gamma 0, what's left, right, sigma 1 times gamma 0 is gamma 1, gamma 0, which equals gamma 1, right? So you go from here to there, and that's true for all of these, right? So that is this. So the duality that we're going to be studying now is a duality that of multiplication on the right by gamma 0, and that takes these guys into each other, right? It doesn't take them into its regular duality, we're going to see, right? Regular duality, right multiplication by I, that takes us into the other half of the space-time, right, that they don't have depicted here. I'm trying to make this piece symmetrical to this part of the split. So this is this part that has the other remaining bivectors, the trivectors, and the pseudoscalar. I'm not trying to wipe out what's underneath it, but that duality is still present, right? That sort of divides the two halves of the spacetime. So the spacetime split is driven by the duality that we know. But there's another split between paravectors and four vectors, right, that we call relative frame duality. So this is the proper frame, this is the relative frame, and they're connected by right multiplication by gamma 0, right? So if I take gamma 1 and right multiplied by gamma 0, I get sigma 1. If I take sigma 1 and right multiplied by gamma 0, I get gamma 1. And in this case, they actually do exactly line up. There was that messy problem of minus signs that we have with this duality. It wasn't that messy, but there were some minus signs we had to take care of. Here, we don't worry about those minus signs. There are none, right? Gamma 1 goes directly to gamma 0, and or the scalar unit vector goes directly to the gamma 0 four-vector basis element, and then all of these relative basis vector elements, which are bivectors, go to these grade 1 vectors. And that's through right multiplication by gamma 0. Okay, so that's actually a lot that's important. We're going to start seeing why it's important in our next lesson, but bivector, space-time split, and cross product. So here's where we're going to get some payoff from the work we just did from 3-vector, regular standard 3D geometric algebra. And here you see they use the same example I just did. In fact, they also do it for the magnetic field. And they talk about general bivectors, so this will be very interesting. So we'll do that next time.